Hi, everyone. I hope you all had a great spring break. I'm missing you all in person, but it's nice to be able to still connect with you online. So we're done with chapter 9, and now we're moving on, or sorry, we're skipping chapter 9. We finished chapter 8, and now we're moving on to my favorite chapter, chapter 10, which involves circles. So this is going to be the ins and outs of circles, and I love circles so much because they have amazing properties. They're pretty special and some cool things happen. So this 10.1 involves a lot of vocab, and then we get to learn a lot of relationships that happens within the circle. Friendly reminder, circles aren't polygons because polygons are made up of lines and lines are straight. A circle is one big full arc that's 360 degrees. We're going to learn a lot more about arcs and degrees within circles in this chapter. So let's go ahead and get to it. Okay. So the first thing I want to talk about is just familiarize ourselves with all the vocab in circles, okay? Now, I'm getting my writing tool here. Okay. So the first thing, a circle always has a center, okay? That is the dead center of a circle. And that's, it'll always be named with like a capital letter, okay? And then a circle is made up of a 360-degree arc, which we say is infinite points made within this arc, okay? And then there's nothing on the inside. So a circle is really just this arc around the center. So first thing first, so this circle here is called circle P. This is this is shorthand for a circle, and it's called circle P. So you would see usually a P here right by the center, okay? So our first vocab word would be radius. I know you guys have seen that word before. True definition of a radius comes from the center to the end of the circle, any point on the circle. So there are infinite radii is plural, in the circle. Next word would be a chord. So I like to think of a chord like a guitar chord, okay? So it's a string from one end to the next, and they're tied up. So a chord just hits one end of the circle to another. So there are actually infinite chords in a circle, and I'm going to draw a few more. So first of all, chords are straight. So let me actually undo that and get a little more particular with this. So chords are straight, and they go from one end to the next. So as long as you're going through the circle and stopping at both ends, that is a chord. So these are all chords. So hopefully you're thinking, hey, is a diameter a chord? Yes, it is. It's a very special chord. It's a chord that goes through the center. So let me move this. So a diameter is the special chord that goes exactly through the center. And then you guys also know a diameter is made up of two radii. Oh, going a little fast. Okay, let me clear the screen and let's get to the next. Okay, so probably this slide would be words you haven't seen before, or maybe haven't seen with a circle. So this is still circle P, that's the name of this image. And the word secant, okay, so a secant is, if I were to define it, I would call it a chord that doesn't, that's how I would call a secant. So chords are tied up at the end, and in this case, it's a line, which lines go on in both directions, that intersects the circle in 2 points. Okay, so it's just a chord that doesn't stop. Chords stop, secants go on forever in both directions. A point of tangency is very special. So the word tangent, I know we learned that in trig, and tangent in the English language, you know, if you're talking to somebody and they get off track and they went on to a different subject, you might say, oh, I went off on a tangent. That means you were going somewhere, you're talking about something, and then you hit a point and started going somewhere else. So that's a point of tangency. Okay, so a circle, when you have a tangency, that means you align a segment, a chord, something hits the circle just once. So a tangent is a line or a ray or a segment that intersects the circle at exactly one point. That point that it's hitting is called the point of tangency. So nice easy names to go with the vocab words. Okay, and then there's your definition of the point of tangency. Let's keep going. Friendly reminder, you can pause this video at any time to take your notes and then just push play to continue going, and just like we were in class. Okay, so this next slide, tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. Notice they're calling it circle C. You can see C in the center of the circle at the center point. So this is a good time to pause and try and name all the vocab words you see here. Once you try to name them, push play and we're going to name them together. Okay, so they want me to name segment AC. So I see segment AC is coming from the end of a circle to the center. So that's going to be a radius. Segment AB goes from one end to the next. So I can call this a chord, but even more special and more specific, I would call it a diameter because it goes through the center of the circle. So the best word here would be actually to call it a diameter, but being a chord is also correct. Okay, so ray DE. Seem to have lost my mouse here. Sorry guys, some technical difficulties. My mouse disappeared on me. Okay, so I figured out, I found my mouse again. Okay, so we were naming our segments and pieces. So AC was a radius. AB could be a chord, or like we said, a diameter, which would be a better word. Now ray DE, it's coming from D, headed towards E. So I can see that it's hitting the circle once, so I would call it a tangent. Line AE, now line AE, it's hitting A and it's hitting G and it's continuing on, so it's hitting my circle twice, so I would call this a secant. Okay, now for the challenging ones, they're asking for segment AG. Segment AG, now be very careful because they said segment AG, that means they're starting at A and ending at G and not going through, so I would call that a chord. Okay, now actually I want to make up a new example here. If they asked for line AG, so line AG, okay, notice I'm putting the line symbol. So line AG tells me it's going through the circle twice and doesn't stop. That would make it a secant. So please know the difference between the two. And then they're saying segment CB, so it starts at the center and hits an end, so that would be a radius. Okay, tangent and tangent segment down here. So a tangent is a line going through, like, DE is a tangent, and then a tangent segment would just be segment DE, and that would mean it stops. So tangent lines or tangent segments are what go through circles if they hit it once. Okay, so I'm going to clear my screen here. Now they're asking us to find the given lengths of the given circles here. So this is obviously on a coordinate plane, okay? Don't freak out here because this will be a relatively easy. It's just testing your ability to be able to count, to be perfectly honest. So why don't you pause it and try to find A through D and then push play to see if your answers are correct. Okay, so the radius of circle A, so here's A. I know this is the center because they're calling it circle A. So simply, you just count. Now to count on a coordinate plane, you always go vertically or horizontally, okay? So I'm gonna go vertically, which would be 1, 2, 3. You can also go horizontal, 1, 2, 3. Remember, just never cut through because that wouldn't be an exact count. So my radius of circle A is 3 units. My diameter of circle A should be twice as big. It should be 6 units. You could also count it 1, 2, 3, 4, 5, 6. It'll also be double. It's always your double your radius. Okay, radius of circle B would be 2 units. And then diameter of circle B is 4 units. Don't make these harder than they look, even though it's on a coordinate plane. These are relatively easy. Okay, find the radius and diameter of circle C and circle D. Okay, so circle D is simply just sitting in circle C. Circle D is here, and it obviously ends at the black arc. So circle D would be 2 units for the radius and 4 units for diameter. 2 unit radius, 4 unit diameter. Okay, circle C would be circle C would be 3 unit radius and then a 6 unit diameter. And you can also see circle C is the same as circle A. They look congruent. Okay, let's keep going from here. My mouse keeps wanting to disappear on me, which is oh so frustrating. So I need to find it back here. There we go. Okay. Clear my screen and go to our next slide. All right, coplanar circles. Remember, plane is sharing, like a plane is a surface. So these would be 2 circles maybe on the same surface, okay? So there are 3 variations of coplanar circles. They could intersect twice, once, or never. So these are the examples of when they intersect. So this first example would be when they intersect twice. This looks like your typical Venn diagram. So they're just overlapping and you can see their point of intersections in red. Okay. If they intersect once, these are coplanar circles that are tangent circles because they're hitting once. So when we say tangent, that means hit once. And then if they're never hitting, you know, you would say they share no points of intersection. So there's 2 different examples here, and I kind of want to note the difference between these 2. So these never intersect. These are just 2 circles on the same plane hanging out. And then this one here, these are 2 circles. One is within the other, and they're sharing a center. This is called a concentric circle. It looks like a dartboard. I've actually seen this question on the SATs and ACTs, the word concentric. So just try to practice that word, get it in your memory. It's a dartboard, and concentric means where they're sharing a common center. They're not going to intersect, but they're definitely sharing something very special, the center. All right, let's clear this drawing and go to our next slide. If I know you guys at all, I know you're doing great, so keep up the good work. And as you know, you can email me anytime for questions, and I would love to help you. I can make you your own little video and help you with your homework. You just got to reach out to me, and I'm here for you. Okay, so here is where we talk about common tangents, okay? And then this is where we're going to have 2 circles in some sort of variation, and we're going to try and draw a line, a ray, or a segment that hits each circle once, so that is tangent to both circles at the same time. We call it a common tangent. So if you look here on the left, you've got 2 circles in a plane, and you've got a line tangent to both circles. They're sharing a tangent line. It's a common tangent. Okay, here on the right, here's another example of a common tangent. So what I'm actually going to do is I'm going to draw all the common tangents that are possible when you have circles in this sort of situation. So you've got a line coming this way. You can have a line coming, it's a little hard to, I'm going to erase that line and let me undo that and try it again. Let me see, I'll start on the circle. Okay, so then there's your second common tangent. Pretend it's not going through the circle, that makes it a secant. Please pretend it's just hitting once. Here's your third common tangent, and here's your fourth common tangent. So when circles aren't touching, they're going to have 4 common tangents. This would have the same 1, 2. I'm counting this one obviously up top. and then 3, and then, ooh, I don't like that one. Undo it, and then 4. Ooh, it's not good that it's going through the circle, so I'm actually going to undo it. It shouldn't even be going through this circle either. It's just hard for me to get that right angle. Here we go, that perfect angle. So that would have 4 common tangents as well. Okay, so on the next slide, you're going to practice common tangents. Tell how many common tangents the circle have and draw them. Okay, so go ahead and pause it and try and drawing your common tangents on these. Okay, so for circle A, or sorry, for example A, the circles aren't touching. So if they're not touching, you should expect 4 common tangents. That was like our last 2 examples on the previous slide. You'd have 1 up top, 2 on the bottom. So you got 1, 2, and then crisscrossing. Ugh, it's so hard for me to get that line. 3 and 4. So 1, 2, 3, 4. Again, it should not be going through the circle. It's very hard for me to get this perfect line here. Okay, I'm going to skip B because actually I think B is the trickiest. I'm actually going to go to C. So hold on. So A has 4 common tangents. Okay, let me write the number 4 here. So you should expect 4. That will always be the case for 2 circles not touching. Okay, so for C, our common tangents, the only way you can go about it is, ooh, I should use the line tool. Okay, so let me undo that. Okay, so we would have 1 and 2. There's no way for me to go through because then that wouldn't be a tangent anymore. It'd be going through all that, and that would become a secant. So if your circles are overlapping like this, like a typical Venn diagram, you only have 2 common tangents. Okay, so B is tangent circles. I'm actually going to write that. Tangent circles, because they're hitting just once, and they're hitting right there at the point of tangency. Okay, so that's why we call them tangent circles. So to draw my common tangents here, there are going to be 1, 2, and then 3. So this one has a sneaky little one that would be going through here, hitting once each circle at the point of tangency. So this would have 3 common tangents. Okay, these are the only options you would have for circles. So you should always expect either 4, 3, or 2 common tangents, just depending on where the circles are within the plane. All right, let's keep going. You guys are doing great. And then there's the answers. Look at their drawings, much better than mine. So there we go. Let's keep going. Tell how many common tangents the circles have here, and let's draw them. So go ahead and pause and give these a try. Okay. So for A, if they're overlapping, the only variation I can have is up top and down below. I can't come through, so I should only expect 2 common tangents for number 4. For number 5, these are tangent circles, but they just happen to be within each other. I would not call these concentric. Okay, 6 would be concentric because they're sharing a center. But 5, they're not sharing a center. You know, you'd have a center here and perhaps here. So I would not call these concentric. It's just one circle within another. I would call these tangent circles. In fact, let me write this. These are definitely tangent circles. They're hitting once. Okay, so, oh no, I lost my mouse again. Every good time I go to text, I lose my mouse. Okay, got my mouse back. So let's go ahead and draw how many tangents we have here. We would only have 1. That's the only way for you to hit both circles at the same time. Okay. And then number 6, if they're concentric, the circles aren't touching each other, and there's no way for me to draw a line from one circle to the next without going through it. So this one would have 0. Okay, so this would have 0 common tangents. Okay. Now let me clear our screen. Let's get to a theorem. So this is a really, really important theorem. It comes up a lot, okay? Now, a tangent line is always going to be perpendicular to the radius that hits it. Now remember, a radius comes from the center to the end of a circle. So wherever there is a radius, I'm going to draw a radius. So there's a radius, and this would be your point of tangency. The line that goes through and hits that point of tangency, ooh, that is a terrible line. Let me use my line tool. So wherever your line goes through and hits that point of tangency, you should expect there to always be a right angle between the radius and the line of tangency. Okay, that's a very, very important thing that's going to come up quite a bit. So always expect a perpendicular between the two. Okay, so here's our first example. In the diagram, segment PT is a radius of circle P. Okay, I can see that. They wouldn't have to say that for me to know that. Is segment ST tangent to circle P? Okay, whenever I hear the word tangent to a circle, my first reaction is the only way for it to be tangent is if this were a right angle. Okay, now they're asking me if it's tangent. So for the only way for me to prove if this were a right angle is if this satisfied, dun, 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 Pythagorean theorem, because that's how I can prove it's a right triangle. So I can see I have a triangle here, okay? So what I'm going to do is simply do Pythagorean theorem. If it works, yes, this would be a point of tangency. So let's go ahead and do it. Now, first of all, make sure you identify the longest side. That would be your hypotenuse. Okay, that would be your C value. So we're going to see 35 squared plus 12 squared. Is that going to equal 37 squared? Okay, so I have my calculator here, and I'm going to calculate it because I don't know 35 squared. Okay, 35 squared is 1225. I keep losing my mouse. That is so frustrating. It keeps disappearing on my screen. Sorry, guys. There it is. It's back. Okay. So 35 squared was 1225. 12 squared is 144. And then 37 squared is, I don't know that. Let's see. It's 1369. So 1225 plus 144 is 1369. So you would have 1369 equals 1369. So yes, this satisfied Pythagorean theorem. So then that means it is a right triangle. Okay, so if it is a right triangle, then that means it is tangent to circle P. So our answer here is yes. Okay, getting my mouse back. Beyond frustrating here. Okay, let me clear the screen. So this would be a more challenging problem involving the same idea, okay? They're asking in the diagram in the diagram, point B is a point of tangency. So that means this line AB is tangent to the circle. So it is a right angle here because they declared it a point of tangency. Find the radius of R. Okay, so I'm going to go ahead and jump into this one because this one's a little more complex. There's examples later that you can pause and try on your own first, okay? So let me draw the right angle where it would be. It would go right here, okay, because B is a point of tangency to the radius. So that means this is my hypotenuse, okay? So that length here would be 50 plus R. So yes, that's how I have to write it. So I'm going to use Pythagorean theorem, and I'm going to say 80 squared plus r squared equals, now instead of 50 plus r, I'm going to say r plus 50. I like to have my variable first. R plus 50, yes, quantity squared. Okay. So 80 squared would be 6,400. R squared is r squared. And then guys, when you get to this quantity squared, you cannot distribute the 2 through. What you have to do is you have to FOIL it. So think back to algebra where you have to rewrite it and you're simply FOILing it. Okay, please do not distribute the 2. You'd be totally wrong. It would ruin your whole problem. I don't want that to happen. So what I'm doing is I rewrote it so that I could distribute. So I would say that's r squared plus 50r plus another 50r and then 50 times 50 is 2,500. Okay, now I would say the hard part's done. Now I just need to combine like terms and clean things up, okay? Don't be afraid of the r squareds. They're actually going to cancel each other out. So 6,400. Now, if you subtracted r squareds before combining like terms, you'd see they just go away. So let's go ahead and just get rid of those. Goodbye, r squareds. We wanted you anyways. So 6,400 equals, so those are gone. I'm going to cross them out. 50 plus 50 is 100r. And then plus 2,500. Okay, so now I'm just using algebra and simply cleaning up. So my next step would be to subtract 2,500 from both sides. Okay, subtracting 2,500. So 6,400 minus 2,500 is 3,900. So that would be 3,900 equals 100r. Now, then I'm getting r by itself, so you would just divide by 100. So r would be 39. Whew. That's some serious algebra there. Okay, this is a very typical common problem. So this is definitely one you want to know how to do. So you're going to see this on a next example. You're going to see this on your homework. So we're going to practice this again, okay? They wanted the radius of r. R is 39. That one's a lot of work, but it's a satisfying one. Okay. So let's go ahead and clear this screen and get to our next example. We'll have more examples like that in a second. Let's go ahead and bring up, tangent segments, okay? So a tangent segment is, so point T is a tangent and point R is a tangent. They're both tangent to circle P. And these are both lines that are going on and both lines are intersecting at S. Okay, so we're calling them common external. So S is a common external point. Okay, so what we know about this is these segments are congruent. Okay, so if you have two tangents coming in, a tangent coming in from the top of the circle and a tangent coming in from anywhere else on the circle, whatever segments get created, those will always be congruent. So that's not so bad. So here we have an example here. They're saying RS is tangent to circle C, okay? And RT is tangent to circle C. Cool, they're both tangent. That's great. The minute I hear that and I see that these tangent lines are intersecting, I know right away that these segments are congruent. Okay, so then that means I can set them equal to each other. They want me to find X. Well, that's easy. So I'm just set it equal to 28. And then I'll subtract 4. So that would be 24 is 3x. Okay, then I'm going to divide by a 3. 24 divided by 3, that would be an 8. So 8 is x. And that's what they wanted. Okay, so whenever you see two tangent lines intersecting, you know those segments created are then equal. That one's an easier one. I like these. Okay, here's a good time to pause it and try these 3 examples. Obviously, when you push play again, you know I'm going to do them with you. All right, so let's see. Number 7 is DE tangent to circle C. Okay, this has a lot going on. This is actually a little bit challenging, so be very careful, but there's always a trick involved. So first of all, is DE tangent? So they're asking me, is this a right angle? Okay, that's what they're asking me. So then that would mean I would do Pythagorean theorem. I lost my mouse again. Every time I pick up my finger, I lose my mouse. Okay, it's back. So they're asking me if this is a right triangle. Okay, now a common mistake people would do is they would say, oh, so 3 squared plus 4 squared equals 2 squared. Well, okay, first of all, 2 is too small to be the hypotenuse because the hypotenuse is always the biggest length. 2 is also in the center of this segment. So 2 means it's just the length of this outer segment here, okay? Numbers always float in the center of the segment they represent. So 4 is this length here, 3 is this length here, 2 is just this length. So we actually need this length here. They didn't give it to us. Ah, but they did. Remember, there's infinite radii in a circle, okay? Never forget that. If you know the radius in one circle, you know the radius in all other points of that circle. So because I see that this is 3, this is also 3. This comes up a lot, so please be careful with that and don't be tricked by it. So guys, your hypotenuse is 3 plus 2, which is 5. So let me go ahead and fix my equation here, okay? Always look for radius and mark it up. We're going to try and trick you like that. All right, so 3 squared plus 4 squared is 5 squared. Well, first of all, I recognize this as being a triplet, your 3, 4, 5 triplet, so I know that 9 plus 16 is 25. So this is going to work. So this is yes. Is DE tangent to circle C? Yes, it does make a right triangle because it's a 3, 4, 5 right triangle. Okay, so let's draw a line. Let's do a different color for 8. Is ST tangent to circle Q? Or sorry, not is. ST is tangent to circle Q, and they want me to find the value of R. Okay, so this is where I'm going to do Pythagorean theorem. This is your right angle. So this here's your hypotenuse, okay, which would be R plus 18. So I would go R squared plus 24 squared equals R plus 18 quantity squared. Now guys, there's no shortcut here. If there were, you know, I'd give it to you in 2 seconds. There's not. It's always going to be this way. And, you know, quite frankly, the annoying part is you have to FOIL it, but FOILing's not horrible. It just takes time. So just embrace it. There's no way around it. Okay, now I'm going to clean it up. R squared plus, so 24 squared is 576. Okay. And then I'm going to go ahead and FOIL R plus 18. So I just like to rewrite R plus 18. Okay. And then I simply FOIL it. So R times R is R squared. All right. And then R times 18 is 18R. You know that's going to happen twice. So 18 plus 18 is 36R. So that's a shortcut if you want to do that. Otherwise, you write 18R plus 18R. It doesn't matter. And then 18 times 18 is, I don't know that, that's 324. Okay, so here's the beauty with these problems, and this is always going to happen. Your R squareds are always going to cancel it out. Now they're calling it R for radius, okay? Look at R squared on both sides. They're literally going to cancel each other out because you subtract them out. Bye, so you don't have to deal with that. So now you're just solving for R here. So I'm going to subtract 324. subtracting 324 from both sides. So 576 minus 324 is 252. So I have 252 equals 36R. Okay, so then I'm going to divide by a 36, and then that'll give me R. So 252 divided by 36 gives me 7. So R is 7. So guys, friendly reminder to check your work. You could always plug 7 back in here. Okay, so that would be 7. 7 plus 18 is 25. So this gives me a 7, 24, 25 right triangle. That's a famous triplet. So you could plug it back in and do Pythagorean theorem, or recognize that it's a triplet and feel good about your answer. Okay, number 9. It's a terrible line I drew through. You get the point. I'm trying to make space for the last problem. Let's choose green. Okay, so here you've got 2 point of tangencies. I can see that because they're right angles from the radius to the tangent line. So that allows me to set x squared equal to 9. Okay, so x squared is not equal to 9. Okay, so this one's nice. Simply just square root both sides. So remember, the square root of 9 is plus or minus 3. And yes, -3 does work here, because when you plug it back in, you get a positive. So there are 2 answers here, okay? Because -3 doesn't represent the length, it represents the variable when you plug it back in. So this is definitely the meat and potatoes of this section, okay? You want to know how to master these. You'll see these at the end of your homework assigned to this. And please practice it, and of course ask me any questions you have involving it, and I'm happy to make a little video and help you through it. All right, I'm going to clear this screen. And we've come to the conclusion. Your homework, page 655, 3 through 10 all, and 15 through 26 all. It's all in both cases because these are really good examples and I want you to master it, okay? So 3 through 10 is vocab, 15 through 26 is more of the algebra math problems, okay? You can always check your answers on Slader, in the back of the book, and of course email me anytime with any questions. Thank you guys, this was fun, and I hope you have a great day.